Welcome, everybody, and good afternoon, both to those who are Zooming in from home or office on this beautiful sunny day in Toronto, or as well as the group that's gathered live stream at the Mars building. And I understand there are a few people there today. For those who don't know me, my name's Sheila McElwraith. I'm a professor in the Computer Science Department at the University of Toronto, a Canada CFAR AI chair at the Vector Institute, and also associate director at the Schwartz Reisman Institute for Technology and Society. Before we begin, as we do with all of our seminars, we want to take a moment to acknowledge the land on which the University of Toronto operates. For thousands of years, Toronto has been the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of the Credit. These and other Indigenous peoples across Turtle Island developed complex and effective governance systems based on respect for all life and the intelligence of the natural world. Today, this land is still home to many Indigenous people who are working to reclaim their rights to self-determination and self-governance, and we are grateful to have the opportunity to live and work on this land. Although we may all be joining from different places today, we encourage you to reflect on the history and relations of the land that you live and work on. So a few logistics before we begin. Of course, as with all of our seminars, this session is being recorded. I just wanted to remind everybody of that. Priya will be speaking probably for about 50 minutes, but that's up to her. Priya, don't feel you're too firmly on the clock. But she has also graciously agreed to be interrupted should there be some burning question or clarification. And she can elaborate, but I believe that what she'd like you to do, if you do want to ask a question during her talk, is to write your question in the chat, and she'll be monitoring the chat while she speaks. After her talk, there will be a question and answer portion, and I would ask you to raise hands, and we'll be following the order, and I will be monitoring it. So with that in mind, it's my tremendous pleasure to introduce today's speaker, Priya Donti, the co-founder and executive director of Climate Change AI, CCAI, an initiative to catalyze impactful work at the intersection of climate change and machine learning. And she's also, Priya's an incoming assistant professor at MIT's Department of Computer Science and Electrical Engineering. Priya's research focuses on machine learning for forecasting, optimization, and control in high renewables power grids, exploring methods to incorporate the physics and hard constraints associated with electric power systems into deep learning models. Priya is a recipient of the MIT Technology Review's 2021 35 Innovators Under 35 Award. She's a former U.S. Department of Energy Computational Science Graduate Fellow, a Siebel Scholar, an NSF Graduate Research Fellow, and a Thompson J. Watson Fellow. She received her PhD in Computer Science and Public Policy from Carnegie Mellon University. So without further ado, Priya, over to you. The floor is yours. And welcome.
Awesome. Yeah, thanks, Sheila, for the really kind introduction, and Liv also for helping with the organization on this side as well. So can everyone see my screen here?
Yes.
Great.
That's good.
All right. So as Sheila mentioned, I'm going to dive in, and I'm very happy to take questions. I would love to take questions during the talk itself. I would love for this to be as interactive as possible. Given the size of the group, both actually, to sort of amend what Sheila mentioned, either feel free to drop your questions in the chat or feel free to even raise your hand during the presentation itself, and we can hopefully iterate that way. So anyway, today I want to talk about the relationship between climate change and machine learning. So, climate change is one of the most pressing issues that we as a society are facing today, and we're already feeling its effects, from storms to droughts to fires to flooding. These impacts are being felt globally, and they are disproportionately being felt by the world's most disadvantaged populations, which creates a real imperative to act quickly on this issue. In particular, according to the UN Intergovernmental Panel on Climate Change, we as a society need to hit net zero greenhouse gas emissions by 2050 in order to stave off some of the worst impacts of climate change. But this is in a situation where emissions are still increasing year upon year, with maybe a slight dip due to COVID, but it's rebounded since then. And as a result, really, there's even more of an imperative to get those emissions down each year. And when we talk about addressing climate change or rapidly addressing climate change, there are actually a couple of different axes of action that we tend to be referring to. So one of these is climate change mitigation, which means reducing or preventing greenhouse gas emissions. So on the slide here, you see basically a breakdown of where the greenhouse gas emissions came by sector in 2019. And what you can see is that there's no one sector that is responsible for even a majority of the greenhouse gas emissions. They come from across energy supply, agriculture, forestry, and land use. That's what that AFL-U acronym is. Industry, transportation, buildings, a lot of different places. And so climate change mitigation entails deeply reducing the greenhouse gas emissions actually created in these different sectors, as well as figuring out how we actually maybe get some of the greenhouse gas emissions that are already in the atmosphere out. The other major axis of action that people tend to talk about is climate change adaptation, which means responding to the effects of a changing climate. So given that we already have put some amount of greenhouse gas emissions into the atmosphere, and we will continue to do so, in some sense, we've locked in some amount of climate change already. And so adapting to this means taking sort of local actions at a global scale. The effects of climate change will be felt differently in different places around the world. And so different places will have to take different actions to actually adapt to climate change. And this will require rethinking, how do we make our food systems more resilient, our health systems, our infrastructure, biodiversity, and our ecosystems. It requires thinking broadly about a combination of our sort of human systems and our engineered systems, as well as our ecosystems. And both of these axes of action are extremely important, both deep, rapid climate change mitigation actions, as well as really robust adaptation actions. And the reason I bring this up is because some people will come to me and say, hey, net zero by 2050, that's a really ambitious goal. Are we going to hit it? And if we're not going to hit it, should we even try? And the answer is yes, right? Every kind of unit of greenhouse gas emission we prevent putting into the atmosphere early on is sort of we're going to get kind of sort of better outcomes with respect to climate change. So for every unit of greenhouse gas emissions that we actually prevent. And so climate change is not an on and off switch. It's one in which we definitely have to act very rapidly to mitigate climate change and actually reduce the extent to which the climate changes. And also one in which we then adapt to the effects that we do face. But it's not sort of we don't hit a certain date, you don't do anything. Definitely there's a lot to be done. So that's the climate change picture, but how does AI factor in, right? When we talk about the relationship between AI and climate change, what do we actually mean? And during today's talk, I actually want to talk about maybe 4 different ways in which AI and climate change are actually related to each other. The first, which I'll spend the most time on, is how AI can help to address climate change, how it can actually help support and strengthen and potentially accelerate some of these applications in climate change mitigation and adaptation, as I talked about on the last slide. At the same time, AI and machine learning technologies are general purpose technologies. They can be used for a wide variety of applications, and they are directly and in large volume also being used for applications that increase greenhouse gas emissions or otherwise sort of, stall the transition to cleaner sources of energy, for example. In addition, there are lots of applications of AI and machine learning that we don't tend to immediately think of as connected to climate change, but nonetheless have large systemic impacts across society that in turn then have effects on how we actually, address climate. And so thinking about these kinds of things is also important. And then, of course, AI and machine learning algorithms, they run computations on hardware. Those computations come with electricity usage. The hardware takes, emissions to produce. So there are also, of course, emissions associated with, the actual running and creation of AI and machine learning algorithms in the first place. So I'm going to briefly touch upon, all of these different, relationships or these different axes, but I first want to talk about this, AI applications in climate change mitigation and adaptation. So Diving in, several years ago, a group of us wrote this paper called Tackling Climate Change with Machine Learning that tried to enumerate in, a succinct 100 pages or so, the different ways in which AI and machine learning can contribute to climate action. And there's, Tegan, for example, who is part of Schwartz Reisman also on this paper. So feel free to ask her questions about it as well. And for those who are interested in this topic, I definitely would encourage you to dive into the full paper or into the summaries that are linked at the top of the slide, where you can basically kind of sift through and filter by topic area and by machine learning area different applications in the paper. In that paper, what we basically do is say, okay, as I mentioned before, greenhouse gas emissions come from a bunch of different sectors. They come from electricity systems, from buildings, from farms, from forests, and so forth. And we go through each of these sectors to talk about where AI and machine learning can potentially play a role. We also talk about the role of AI and machine learning in adapting to climate change. So again, strengthening our human systems, our infrastructural systems, and our ecosystems. And also where AI and machine learning play a role in strengthening policy, in organizational decision-making, individual decision-making, all of the kind of decision-making frameworks that are required to actually get climate change mitigation and adaptation strategies off the ground. And so while I'm not going to be able to talk through, every single application that we talk about in the paper in the span of this talk, what I hope to do over the next few minutes is give a sense of some of the themes that emerged across these different applications to just give a mental model for where AI and machine learning and what kinds of ways these technologies can play a role. So the first of these is gathering information. So there are many places where we're starting to see, large streams of raw data becoming available, things like satellite imagery or online databases that collect all of, many of the world's policy documents. And these large sources of data, they contain a lot of information, but often too much information to be parsed manually. And so many AI and machine learning algorithms in the climate change space have focused on how do we turn these large raw streams of data into actionable insights that somebody can actually do something with. So for example, the figure on the slide comes from a paper and an effort that actually uses satellite imagery to understand the crop cover, the sort of what crops are present, how much of the crop are present on a particular parcel of land. And the goal there is to guide farmers who are trying to adapt to the effects of climate change as to, how do we see the crop yields changing over time? How does that correspond to climate change related effects? And what insight can that give us about what we need to do to actually adapt agriculture in a more robust way? Similarly, there are lots of applications that turn satellite imagery combined with on-the-ground data and other information into these kinds of insights. For example, a coalition of organizations called Climate Trace that provided the sort of first independent inventory of the world's greenhouse gas emissions. So what sectors are producing these emissions and where they're coming from, with the idea of basically informing international climate change negotiations. And similarly, there are efforts to pinpoint deforestation from satellite imagery, to pinpoint where different buildings are, the energy efficiency characteristics of buildings are, in order to inform the city planning efforts and so forth. And there also is a nonprofit called Climate Policy Radar, which is basically trying to aggregate policy documents from around the world, so text documents, and actually analyze those in a way that gives governments who are themselves then trying to make policies insight into what worked in the past and what didn't. In all of these cases, this large scale sort of, inference of, information from these large sources of data is not necessarily a replacement for high quality on the ground data. For instance, if I wanted to understand the energy efficiency characteristics of buildings in my city, ideally the best way to do that would be to put actual, on the ground surveying and instrumentation in your city. But in cases where that's not necessarily feasible, or where it's not feasible to get that high quality information, this kind of, this kind of workflow of turning raw data into proxies for this kind of information can serve as a bit of a stopgap or a way to sort of start making decisions without that more detailed data. So another theme, maybe unsurprisingly, is forecasting. There are lots of situations in which having some kind of foresight about your system or your environment can enable you to make better decisions upfront. So for example, the nonprofit Open Climate Fix develops forecasts of solar power and electricity demand for the UK power system operator in order to help them better balance a power grid with lots of renewables where the amount of renewable energy available changes from moment to moment based on the weather. And having this foresight, having these better forecasts ahead of time can basically help power grid operators, deal with all of the engineering constraints that come with operating a power grid. If they tell a particular power generator to turn on, it's not going to do so. It'll take some time for that to actually happen. So foresight can enable them to make these decisions, with a little more lead time. And similarly, there have been lots of applications of AI and machine learning to, forecast demand for future public transportation, for example, to actually inform the build-outs of public transportation, or also even to forecast extreme events in the future, combined with, taking data plus climate models, for example, to actually forecast these into the future. So both of these themes so far of gathering information and forecasting have to do with turning sort of historical data or large streams of data into insight. There's also another class of applications that deals with actually optimizing operational systems in real time in order to, for example, improve their efficiency. So for example, heating and cooling systems make up about half of the greenhouse gas emissions associated with buildings. And buildings themselves make up something like, depending on how you account for it, 20, 30, some odd % of global greenhouse gas emissions. And so improving the efficiency of heating and cooling systems can be a really big way to actually decrease the greenhouse gas emissions associated with buildings. And so machine learning algorithms have been used to, take in combination of sensor data about a particular building. So that gives them information about, how and when it's being occupied, for example, taking information about the thermal performance characteristics of a building, the weather outside, and sort of intelligently combine this information to provide a way to control your heating and cooling system in a way that maintains thermal comfort or other properties you may want to maintain while reducing the total amount of energy needed to actually maintain those properties. And these kinds of principles come up not just in, residential and commercial buildings, which is where we might think about, but also in places like data centers or in the refrigeration systems that are used to transport food to make sure that the food actually is maintained at, the correct conditions while reducing food waste. Another example of a place where AI machine learning has been used to improve operational efficiency is in the freight transportation sector. So for example, things like, helping to optimize supply chains in ways that actually reduce redundancies and inefficiencies in those and basically cause, fewer, trucks to go out or so forth. Similarly, AI and machine learning in operations are often used for the application of predictive maintenance. So trying to identify a fault in infrastructure either before it occurs or right as it occurs in order to enable that fault to be fixed very quickly. For example, as methane or as natural gas is transported from where it's extracted to where it's, for example, used to for heating or it's used for power generation, it's transported in pipelines. And those pipelines sometimes leak. And when a natural gas pipeline leaks, that puts methane, a really potent greenhouse gas, into the atmosphere, which is something we want to prevent. So various work has looked at, can you actually use sensor data instrumented in the pipelines or aerial imagery or satellite imagery or a combination of these things to actually identify methane leaks either once they occur or before they occur to actually prevent the emission of methane into the atmosphere. Another example, and this is the figure on the slide, this is from Deutsche Bahn, the German train operator, which basically uses machine learning in a variety of workflows to basically try to reduce the faults or breakages or in equipment on the actual rail system in order to reduce the extent to which trains get delayed. And this in turn can actually increase the attractiveness of railways compared to maybe more carbon emitting sources of transportation. And as a result, kind of helped maybe shift various kinds of freight and passenger transportation towards the train sector. So again, these last two themes have to deal with kind of operating a system in real time. Another set of themes that we start to see is in cases where we're not necessarily dealing with a real world system in implementation, but maybe where we're trying to think about, a next generation technology or trying to engineer a new system. How can AI and machine learning actually help us to accelerate these science and engineering workflows? For example, when you're trying to create the next battery, maybe a battery that's good for, being being put on a power grid and actually being charged using renewable energy, or a battery that's going to be used in your electric vehicle. When you're trying to create a battery with the correct properties for that particular application, how somebody would usually do this is they would say, okay, I have some sense of what characteristics I should synthesize this battery to have, how I should actually synthesize this battery. Let me try. Let me then test this out over the course of several months to understand if it works or if it works well. And based on what happens, let me now synthesize a new battery, test it out for a few months again, and repeat the cycle. And as a result, kind of creating a battery can take, many, many months to years, whereas in many cases, we want this to happen much more quickly, right, to facilitate deployment across climate change related workflows. And so AI and machine learning have been used to actually analyze the outcomes of past experiments in order to then suggest what experiments are most fruitful to try next. And by doing that, basically, you can use these technologies to cut down on the number of design cycles that a scientist needs to go through, and as a result, reduce the total amount of time it takes to actually create a battery. And so this paper, this image from on the slide is from a paper that came out of Stanford and actually then ended up spinning out into a startup called Aionics. And this startup basically works with a bunch of different battery manufacturers or battery creation companies to actually speed up their process of actually inventing that next battery. And then a last theme here is approximating time-intensive simulations. So there are lots of climate and energy workflows where you have some kind of large physical model that you're trying to run. And where doing that is extremely time-intensive and energy-intensive as well. For example, this comes up in climate modeling, where you're actually trying to, of course, model what the climate is going to look like in the future. That's a huge system to be modeling. It comes up in energy systems, where you're trying to resolve the physics of the power grid. And it also comes up in areas like city planning, where you maybe want to understand how the wind flows through your city based on where the buildings are and how you actually design the buildings, because that affects the overall energy usage of these buildings. And resolving these physical simulations can take a lot of time. And so machine learning has been used in various places to try to, where possible, approximate portions of these simulations so that the overall simulation can run faster. And a simulation that runs faster, or that is less computationally intensive to run, can be, run more. So for example, you can evaluate more scenarios if you're trying to figure out what the best policy is going to be. Or for example, you can increase the spatial granularity of it. A simulation that you maybe were only able to run that could tell you something about the climate impacts on a very large region, you can maybe now look at that in a smaller setting. And so the paper on this, the figure on the slide is from a paper that basically tried to approximate or create approximate models for cloud physics in order to then embed those into larger climate models. And as a result, the overall climate model would hopefully run faster. So these are some, examples of themes through which AI and machine learning can, address climate change mitigation and adaptation. And again, the applications that I talked about aren't exhaustive, but hopefully this gives you a sense of the kinds of things that AI and machine learning technologies can do here. There are both, many things that you can do today with these technologies. So there's a lot of existing stuff that can just be deployed today and is being deployed today. But also for those, AI and machine learning researchers in the room, there's also a lot of opportunity for innovation. For example, many climate change related workflows require, using physics-informed methods or methods that enforce some notion of robustness that is important for that climate change related area. Many of these that are used in, for example, policy-related workflows require some amount of interpretability so that policymakers can understand when something goes wrong, why did that happen? Similarly, uncertainty quantification is really important, and there are lots of directions in generalization and causality that come up as you try to, figure out how machine learning is, figure out patterns that maybe are occurring in one region and try to figure out how much can I actually bring that to bear on another region. And in general, I would say that the directions, the demands of the climate change related domain need to shape the directions of the innovations that occur. So for example, when we talk about robust machine learning, this is something that it's sort of a established area in machine learning, both in the context of adversarially robust machine learning and safe reinforcement learning. But the notions of robustness or the notions of safety that are used in those areas are actually implicitly tuned towards, for example, the things that we need for images or text, the sort of standard kinds of things that we tend to think about in machine learning. And they're not necessarily taking into account the notions of robustness that, for example, are necessary on a power grid. And so thinking through what are the actual demands of the climate change domain that I'm thinking about? What does it mean to be robust in the context of a power grid? And then using those demands to actually shape the way that you think about, for example, robust machine learning can be a really powerful way to move the methods forward, but in a direction that serves a broader set of domains and fields than our current methods serve. And for those who are interested in this and want to see this dived into in more detail, I'd encourage you to check out the ICML tutorial that I and some others gave that tried to actually dive into some of these methodological directions that we find interesting in this area. So given that broad overview, I wanted to dive in and give one example of sort of the ways in which the demands of a particular domain might shape the way in which you innovate on machine learning by talking a little bit about my own work. Specifically, my own work focuses on how AI and machine learning can be used to more effectively optimize power grids in order to improve the ability to integrate renewable energy. And in order to do this, you have to basically deal with the fact that power grids and a lot of climate and a lot of other climate energy workflows have a lot of physics, hard constraints, and decision-making procedures that you must satisfy when working in these systems. So I want to dive into a little bit about, what these physics and hard constraints actually are in a power grid and how maybe that informs the way in which one might actually develop a machine learning method that operates in these systems. So electric power grids contribute about 1/4 of global greenhouse gas emissions, and reducing these emissions is going to require incorporating more and more low carbon energy. That includes solar and wind energy, basically forms of renewable energy that whose output varies based on the weather. And when power system operators are trying to actually manage a power grid that has, a lot of different power generation sources on it, they're trying to maintain this balance between power supply and power demand at every moment in time. And if that balance goes out of whack, then you basically start to get some faults and potential blackouts on the system. And in particular, when they're doing this, they're dealing with many different notions of physics and hard constraints. So when I talk about electric power systems, I should also back up. When I talk about electric power systems, what I'm talking about is the system through which our electricity is produced, then transported along lines and electrical equipment, and then actually then consumed by end-use consumers like us. And again, on the system, there are various types of physics and hard constraints that we need to deal with when actually managing the system. So for example, when you put power into the power grid, it flows along the lines according to various physical laws. There are also various constraints on the equipment on the power grid. So if I tell a power generator to power up, it takes a certain amount of time for it to do that. And that's usually not negotiable. It just is an engineering system. It takes some time to power up. And there are also various kinds of stability constraints that we need to satisfy to make sure that the power grid doesn't go too far from some kind of electrical equilibrium. And then in addition to these physics and hard constraints, there are lots of decisions that are made constantly on the power grid. So for example, given some forecast of electricity demand, and given these hard constraints, how do we schedule electricity supply in a way that maintains all of these hard constraints and also, for example, reduces costs, make sure that the power is not too expensive for everybody? So there are lots of traditional methods from optimization and control that are used in these power grids to help with this decision-making under these physical constraints. But the challenge is, as we start to need to more dynamically manage power grids to deal with the real-time variations that come from renewables, these existing methods are really struggling to deal with that speed and new scale that these systems need to be managed at. And this has, led to some thoughts about, can AI, machine learning, and other data-driven methods actually, play in the system and help us actually surmount these challenges? So, for example, it's been, hypothesized, can AI and machine learning help us adaptively control different components on the power grid? So, power generators, inverters, batteries, in ways that are actually able to accommodate real-time things that are happening on the system. So how much solar and wind is actually being produced in real time. And AI and machine learning algorithms are proposed for this because they're really good at doing things that are dynamic and data-driven and in real time. But the limitations with existing methods are that they have a lot of difficulty enforcing physics and hard constraints of the sort that I kind of talked through just now. So this is the challenge, right? How do you actually get methods that can deal with that can be dynamic and data-driven in the way that we need them to be, but preserve these properties of existing methods in terms of enforcing physical constraints? Similarly, AI and machine learning are pretty routinely used for predicting electricity demand on power grids because of their strengths in time series forecasting, for example. But a limitation is that these forecasting methods are often kind of developed in a little bit of a sandbox. They're developed to be as accurate as possible without any cognizance of how is this forecast actually going to be used to make a decision downstream. And certain types of mistakes are worse than others when you're actually creating a forecast. For example, if you underpredict electricity demand, that has very different implications than over-predicting electricity demand for how a power system operator actually makes decisions. And so training a machine learning model to make a forecast in a kind of decision agnostic manner misses these kinds of decision relevant trade-offs. So a question one might ask is, how do we reap the benefits of AI and machine learning methods in this setting, data-driven, dynamic, and so forth, while mitigating some of these limitations of not being able to account for the physics and hard constraints and domain considerations? And so what my work does is it presents a framework called optimization in the loop AI to actually deal with this. And for those who are familiar with, the literature on optimizing, for example, machine learning methods, things like, through stochastic gradient descent and backpropagation, that's not actually what I'm talking about. What I talk about when I say optimization in the loop AI is basically a framework for developing AI methods that incorporate inherently some knowledge of the physics or hard constraints or decision-making procedures that we need to enforce through the use of optimization problems. So for example, that might look something like this, where you have, for example, a machine learning model, some objective that it is trained to optimize. And we hope that somehow we can embed knowledge of the physics and hard constraints that we care about, either within the model or in the objective function, in order so that this machine learning workflow, again, inherently has some notion of what are the physics, hard constraints, decision-making processes that I need to deal with. And so for those who are really curious, and again, I'm going kind of, deep into the machine learning methods here. The way that my work does this is by providing a framework for embedding optimization problems into neural networks in the form of neural network layers. So for example, we might have a machine learning model that looks like this, where X is the input to the model, H sub theta is the model and its parameters, and then the model has some output and loss function that it's evaluated on. And if our machine learning model is a neural network, we can think of this neural network as a bunch of nonlinear functions with parameters that are composed together in some way, where each of these functions is a layer. And where these, the parameters of these layers are updated using, backpropagation and gradient descent, some kind of gradient-based procedure. And so what my work does is says, well, we need to have this neural network where every single component of the neural network is differentiable, because we need to be able to train it using backpropagation and gradient descent. Can we somehow actually embed an optimization problem as a layer into our neural network, and as a result, give our neural network knowledge of our physics, our hard constraints, through that optimization problem that we're embedding into the neural network. So there's some, technical detail to how that's done, right? Because if you put an optimization layer or any other layer into a neural network, I need to be able to tell you how to take derivatives through it. But that's basically what my work does. How do we actually formulate these physics and hard constraints from a power grid, embed those into a neural network, and figure out how to differentiate through them in a way that plays well with how neural networks are trained. So that was a little bit of a deep dive, right, into a very specific, set of methods. But the key point here is that a lot of applications in the power sector can really benefit from incorporating physics, hard constraints, or domain knowledge in some way. And my work presents one mechanism for doing this by embedding optimization layers into neural networks. But in general, this is a consideration to be thinking about, right? What are the ways in which are the various kinds of, physics constraints, domain knowledge, other domain considerations we need to care about in these climate change domains? How can they actually shape the way that we develop the machine learning methods in the first place? And this applies, not just in electric power systems, even though that's where I just did a deep dive, but this point really applies across a wide variety of sectors in the climate change arena. Okay, so having dived into, both a general overview of where AI can be used to address climate change, but also a very specific, set of applications, I want to kind of zoom back out and talk about some important considerations to think about when using AI and machine learning in this kind of space. In particular, the discourse on responsible AI, I think, has rightfully come more to the forefront over the last several years. And this discourse on responsible AI absolutely applies in the climate action space as well. So for example, when we think about responsible AI, one axis we think about is how can we mitigate biases that occur in the data and the models and the workflows that we actually create in the AI space. And this, again, definitely applies in the climate change space as well. For example, there are lots of initiatives that try to understand the energy efficiency characteristics of buildings, for example, using satellite imagery, and then acts on that to create energy efficiency policy. For example, where should we do retrofits? But it's important to know that the data that we have about buildings and the sort of existing energy efficiency characteristics of these buildings are hugely shaped by histories of, for example, housing discrimination, and access to capital in various parts of the world, and in various sort of, not just parts of the world, but in sort of, different, different sections within even a given city. And it's important to think about how this actually affects the way in which we, perform these workflows. We're actually understanding energy efficiency and making decisions downstream. And similarly, we have, more data about buildings in some regions than others. And so models that are trained to predict building energy efficiency using the existing data we have might do more poorly when predicting in certain regions than others. And this is something we need to be really cognizant of. Similarly, it's not just the data, but there are also many choices we make when actually building models that themselves can, of course, induce various kinds of biases. So for example, when we create weather models, we tend to calibrate them based on data we're seeing on the ground. So we create some kind of weather model that's maybe created using a combination of physics and data. We see how it does, and then see how it does mean we see, okay, in the UK, is this model doing well? And if it's not, how do we actually tune the model in a way that it actually does better in the UK? But this calibration, as a result, tends to get over-optimized for certain regions of the world. And you tend to see these models, for example, not performing well when it comes to, Arctic regions or regions that have different characteristics than where the model was calibrated for. So some of the choices we make when actually building these models actually also entrench various kinds of biases. There are also lots of settings in which, trustworthiness and accountability are required from our AI and machine learning systems. And again, this plays out in climate as well. For example, when we're optimizing a power grid or optimizing some kind of industrial process, notions of safety and robustness become very important. And importantly, the notions of safety and robustness that are salient to that particular domain. And also in policymaking contexts, as I talked about before, interpretability and auditability can also be a really important attribute. When it comes to responsible AI in the climate change space, it's a setting where we both want to think about equity as it pertains to the discussion in the AI and machine learning space, but also there's a huge discourse on equity in the climate change space as well, making sure that a broad variety of communities are empowered to actually participate in the way that we respond to climate change. And as a result, doing responsible AI in this space requires centering diverse stakeholders, even in situations where it might not always be the most immediate or convenient thing to do. For example, industrial agriculture has a lot of money. They fund a lot of research, right, in universities in robotics, for example, to optimize their processes. But smallholder farmers don't often have access to the same capital, to the same talent that industrial agriculture does, just by virtue of who has, seats at job fairs or who is able to fund university research. And so it's important to really think about how the mechanisms that we create around this kind of work, how can we do that in a way that actually enables us to expand the set of stakeholders whose problems we're actually addressing. Of course, AI and machine learning technologies, especially today, a lot of the talent, the compute capacity, the data is concentrated within a select set of entities and geographies. And so thinking about when you're developing these kinds of methods or developing these kinds of workflows, how do you make sure that you don't foster that centralization of power, but instead democratize access to, talent, capacity, compute through the way that these applications are gone about. And then another big aspect here is avoiding what's called digital colonialism. So basically, this refers to situations in which data from, for example, a developing country or developing context is used by an actor in a developed country to create some kind of better algorithm or create some kind of better workflow in a way whose benefits and sort of profits in some sense don't necessarily flow back to the communities whose data was used. And there's a huge danger of this happening. For example, as satellite imagery becomes very ubiquitous, it's very easy to say, okay, someone sitting in the US or Canada can analyze some remote country and come to some conclusions about what's going on there. But that doesn't necessarily involve people on the ground in that area. And they may not actually then benefit from the way in which these things are done. Similarly, when it comes to smart metering, basically the meters that are put on our homes to actually monitor how much electricity that we're using. Different countries have very different protections around how that smart meter data can be used. And so there's a big danger, and this has already started to happen, where researchers actually work with smart meter data in countries where it's easier to get because their countries don't have privacy protections for individuals in the same way, rather than doing it in their own country, but then use that to sell technologies elsewhere. So avoiding this particular paradigm of digital colonialism also becomes very important. Okay, so as I said, most of this talk I focused on applications of AI to address climate change, so in climate change mitigation and adaptation. But as I framed the talk with initially, this is not the only way in which AI affects climate change. There are many other ways, for better or for worse, that AI affects climate change. So one of these is through applications that increase greenhouse gas emissions. So AI is widely used in emissions-intensive industries like oil and gas and mining. For example, a report from Greenpeace noted that AI technologies in some cases have boosted production levels of oil and gases by as much as 5%, and that it has and will generate billions of dollars of revenue for the oil and gas sector. And this basically serves to increase the competitive advantage of oil and gas relative to cleaner alternatives to which we may want to transition, and as a result, potentially has the effect of slowing the energy transition. And again, this is a really big application of AI today. Many of the large tech companies have dedicated initiatives that are trying to foster custom solutions for oil and gas. And it's really important to be cognizant that this is a huge way that our technologies are being used, and to think through how do we actually mitigate these kinds of effects. Now, of course, though, oil and gas is in some ways very easy to pick on, but there are lots of other situations in which, again, something can have a really big systemic impact that we don't initially think of as climate relevant, but actually is very important from a climate perspective. For example, autonomous vehicles are a technology that is very much powered by AI and machine learning, but depending on how autonomous vehicles are developed, they can potentially be good or bad for the climate. For example, if autonomous vehicles are developed in a way that entrenches the role of private fossil fueled transportation, that basically makes those systems be used more. Whereas if autonomous vehicles are developed in a way that fosters public and low carbon transportation, then it potentially facilitates a shift to these public and low carbon systems. So thinking about how the trajectory of autonomous vehicles look, but then as a result, the kinds of problems that we're solving using AI and machine learning to facilitate autonomous vehicles is really important to think about. For example, the kinds of computer vision algorithms or the metrics that we use for evaluation, or the data when we're thinking about a private vehicle versus a quote unquote autonomous people mover, a bus that basically connects between public transportation and where a person would want to end up going. The algorithms end up being a bit different in practice just because of the data you're using, the kinds of things you're detecting, and it's important to be cognizant of this. In addition, AI and machine learning are big powerhouses of the personalized advertising infrastructure around the world. And personalized advertising, of course, serves to try to increase societal consumption in ways that definitely has implications for climate change. In addition, these technologies are often used to facilitate the spread, or to target the spread of information in social media and on search engines, and as a result contribute to the spread of information, but also unfortunately misinformation on these systems. This can increase, for example, polarization around climate change related topics. On the flip side, though, machine learning is also being used for misinformation detection and to try to actually take misinformation about things like climate change, off of social media. So basically, there's a very nuanced way in which these technologies interact with information and misinformation in these settings, and that in turn, again, has bearing on how we as a society approach climate change. And also, there are definitely various ways in which these technologies induce societal power shifts across society, as for example, large tech companies will start vending to small cities and say, hey, we can be your AI and machine learning workforce. And this induces a lot of data collection initiatives in cities, lock into these large solutions providers, and then shifts in the agenda of how actually, these entities actually approach various societal issues, including climate action, because of these societal power shifts. For example, if they're scared to, shift away from a particular data provider because they've been locked into that data provider. It's really important to think about these kinds of effects as well. And in general, these kinds of impacts are really hard to measure, but they're extremely important to account for and to shape, both through the way in which we develop technologies and the way in which we think about governing technologies. And then the last aspect here I'll talk about is, the emissions of AI technologies themselves. So these last three axes had to do with the ways in which AI and machine learning are used. This last axis has to do with basically the computational impacts of running an AI or machine learning algorithm itself. So to try to get a sense of how big this issue is, so on a macro level, data centers account for something like 1 to 4% of electricity consumption, and this number sort of depends. So the 1% on the slide is from the IEA. And this electricity demand of data centers has actually remained roughly constant over the last decade, because even though we're doing much more computation, the hardware has also gotten more efficient. So these trends have roughly, stayed in pace. That said, we can't take this for granted going forward, that if we can't take for granted that hardware will continue getting efficient at the same rate that computation increases. So this is something we definitely need to be looking out for. And the greenhouse gas emissions that are associated with this electricity depend on a few different factors. So they depend on, for example, the amount of electricity that's actually consumed, the carbon intensity of that electricity. So is it coming from renewable sources, for example, or not? And it also depends on the hardware itself, right? What were the emissions associated with actually producing that hardware, with transporting that hardware, and with disposing of that hardware at the end of its life? And the AI and machine learning account for some fraction of these greenhouse gas emissions from data centers, though it's not necessarily clear. Nobody has a really good estimate of what that fraction is. So that's on a macro scale. On a micro scale, thinking about individual AI and machine learning models, the largest AI and machine learning models have grown substantially over the last few years, and they have very large energy requirements associated with them. So there's definitely need to measure and monitor these kinds of trends. These have implications not only for energy consumption and emissions, but also for equity. As it becomes more and more expensive to develop these kinds of models, not everybody can necessarily participate in their creation. And so there are a lot of research considerations to think about here in terms of, how can we create more energy efficient models? How can we create better cost benefit analyses that basically understand, how much is that potential small increase in accuracy in your model actually worth from a practicality perspective? Is it worth the energy that you actually use to get that small additional unit of performance? So thinking about these kinds of things also becomes really important. So to close, basically, given this, general overview of how AI and machine learning affect climate change, one might then think about how do you actually align these technologies with climate change goals? So the first is that when you're doing this kind of work, it's important to consider the emissions impacts of both the applications that your work is being used for and the computation that is being done. Whether you're directly using AI for something that you think is climate relevant, or you're directly using it to facilitate climate action, but even AI and machine learning more broadly, I hope that some of the applications I showed show that even if you're not working on something that's directly climate relevant, it still can have huge impacts for climate change. So thinking about this is really important. It's important to think about the ways in which, the way we think about responsible AI and the way we think about climate justice and climate equity. So the way we think about equity in the climate change space, it's important to think about what are the implications of now using AI in the climate change arena for both of these aspects. And then also, I would say it's really important to communicate responsibly about the strengths and limitations and capabilities and lack thereof of AI and machine learning technologies. Climate change is a really hard problem, and a lot of people are looking for solutions, and they're really looking for something to come in and sometimes save the day. And so if we are not careful about the way in which we communicate about AI and machine learning, this often creates the situation where those from climate change related areas will jump on these, right? Say, oh, of course, we can use these technologies, take them forward. And in some cases, this can cause more harm than good. It can cause flashy technologies to be funded in situations where maybe simple alternatives would not have been funded, but would have been effective instead. So it's really important to think about how we communicate about this. So for those who are interested in, continuing to think about these topics and learn more, I would encourage you to check out the Climate Change AI nonprofit and community. So basically, Climate Change AI does a combination of providing, research and reports and resources to help kind of frame this broader space of climate change and AI. We have various conferences, events, for example, workshops at the major machine learning conferences, alongside mentorship programs for submission to these workshops, a summer school, and events at the UN Climate Change Conference. We run funding programs. For example, recently ran a $2 million grants program funding research at this intersection of climate change and AI, awarded to 13 grantees, including one at U of T. And then we have broadly a online community platform where you can meet others, a newsletter that has calls for submissions, funding opportunities, readings and job postings, webinars, happy hours, places where you can meet others. And so for those who are interested in kind of plugging into this space, meeting others, forming collaborations, and potentially getting some resources for your work, I would definitely encourage you to check out the Climate Change AI community. So with that, thanks so much, everyone, for listening, and I really look forward to the discussion and questions.
Great, thank you very much, Priya. That was a really thought-provoking and interesting talk. I'd like to open the floor for discussions, and so if people can raise their hand, I'll watch the list and call on people as they have questions that they might want to ask. Does anybody have a question that they'd like to start off with? Steve. Oh, Steve Easterbrook. Yeah, thank you. Steve, maybe you can introduce yourself as well. I don't know that you and Priya know each other, but I think for the rest of our audience.
We do indeed know each other. And we got a little shout out at the end there because ours is one of the grants that Priya was talking about. Good to see you again, Priya. And I haven't had a chance to congratulate you on the new position at MIT. That's very exciting.
Thank you.
We like to think of it as America's University of Toronto. Yeah, fabulous talk and lots of ground that you've covered. That's a really nice kind of high level view of a huge range of things that we need doing, all of which needs to be done. So maybe I could start off with a question about how you reconcile the academic work, and nearly everything you've described here focuses on academic work and the activism. And of course, this is in the context where we've reached a point now where governments are declaring a climate emergency. People are describing it as a crisis. It's more than just, will we carry on doing what we're doing? And, you know, and I'm sure I've gone through this, and I'm sure you've gone through it as well. It's like, do we just carry on doing good research and publishing it? Or, you know, do we need to be out in the front line? So I wondered, actually, maybe you can reflect upon that personally, and of course, advice for other people as well. How do you reconcile those?
Yeah, so this is a great question. And I think basically it's important for me anyway, like to think of myself, there's me as a professional, right? Somebody who does research. And then there's me as a person, a citizen of my broader, you know, society. And acting in one realm doesn't preclude me from acting in the other. And so I definitely think about for everybody, right, what you can do in your realm as a researcher through your profession and how you can affect systemic change that way. But then also think about how you can, you know, in your personal life, like through, you know, writing your officials, by, you know, informing people, like how do you actually affect systemic change through your personal life as well? And of course, there's a lot of individual action you can take too, right? A lot of people I talk to, they say, you know, what do you do about climate change? They're like, of course, I deal with my diet. I try to, use low carbon transportation. And this is really, really important to do. But also affecting systemic change is really the thing that needs to happen to create these large scale societal shifts. And again, we can do that both personally and through work. In the research realm itself, I think something that, is a bit of a challenge is that a lot of the research in AI and for climate, it stays research. And this question of how you actually drive pathways to deployment is in some ways a difficult one, because the incentives in research often don't foster that, right? If you want to really drive a pathway to deployment, you should form a really deep collaboration with industry or government or an entity that really is that would actually use this work, and then also figure out how this work actually scales. And often the fast time scales of publication, don't incentivize that. And so I think there, first of all, is a real responsibility, again, thinking of ourselves as affecting systemic change. You can affect systemic change within your research community as well, right? By pushing for these incentives to actually be changed in ways that foster this kind of better work. But then also some of what I'm trying to do, or what in my own research, but also more broadly, what we're trying to do at Climate Change AI is think through what are those additional bottlenecks in moving things from research to deployment, and how do we actually identify those, fill some of those ourselves, and actually get people to come fill in the gaps. And so if that's something anybody on the audience is interested in brainstorming about and contributing to, please reach out, because I think it's obviously super, super important to make sure that this stuff actually gets deployed on the ground. Thanks, Steve.
I have a question, actually. I'm curious about Canada is a particular a large producer of it's an oil-based or a fuel-based economy, and I'm wondering if you can comment on regulations and governance. Fossil fuel, thank you. And what Canada can do specifically in terms of climate, and whether that dovetails with anything that you're doing in AI.
Yeah, that's a great question. And admittedly, I'm like a little less familiar with the sort of Canadian landscape around some of these topics. But I mean, in general, this idea of, how do you frame incentives to move away from fossil fuels is tricky. I mean, it came up even in Germany, where, for example, much earlier than many others, Germany basically incentivized the large-scale installation of solar power through its Energiewende, it's like energy transition initiative, and that created, right, a large-scale rollout of solar, which was fantastic. Around the same time, though, because of the Fukushima incident, they actually announced the closing of Germany's nuclear plants, and that created this kind of, uptick in the amount of coal that was used. And there's also a very strong coal and fossil fuel lobby in Germany. And so you have this country that on the one hand is really motivated to transition, right, is creating these subsidies that many people are like, this is so expensive, why are you spending this money? And they say, because we need to foster the transition. But on the other hand, has these entrenched interests. And there obviously is no easy solution to thinking about this, rather than, as I would say, this is something that I try to act on in my personal sphere, really, pushing and pressuring, policy and legislation to really shift how this works. Yeah.
Yeah, it's tricky. It's tricky here in Canada in particular, and I think some of those types of incentives are things that we're grappling with here as well. Yeah. I actually have a technical. Oh, there's someone in the chat. I don't know.
Yeah, so I think Mary says, like, commenting on the Germany situation, which I agree with. Germany took the plunge and then made political choices that impacted its foresight, and yeah, for sure.
Yeah, that's right. That's right. Yeah, I think many of us are familiar with what's going on in Germany, and nuclear is another, challenging topic. I actually have a couple of technical questions for you, if the crowd doesn't mind. Which is, I'm curious about the nature of in your own work. I'm curious about the nature of the types of domain constraints and hard constraints that are embodied in your optimization, how you incorporate them, and then I'm also sort of generally interested in how easy and accessible these tools are to practitioners or to misuse by practitioners, whether these are actually tools that I'm sure you're aware and cognizant sensitive to this, that we want to make our tools usable by people who are practitioners in the field.
Yeah, absolutely. Those are great questions. So on the first front, in terms of the nature of the constraints, I worked on a couple of different routes that require different constraints. So one of these is coming up with approximate algorithms for power grid optimization. So you have these optimization algorithms that currently dictate, given a certain amount of electricity demand in certain places, how much electricity should be produced by different power generators, across the power grid. And these models these optimization problems are really time intensive to run. So what my work does is say, can we come up with a way to actually approximate this particular optimization problem? But we need to do this in a way that preserves the constraints of the original optimization problem. And here the constraints basically encode two things. They encode limits on how much each power generator can produce, both a minimum and a maximum if it's on. And then they also encode constraints on how much power can flow through different lines in the power grid, and also the fact that the amount of power flowing into any node on the power grid has to exactly equal the amount of power flowing out. So you have sort of like a conservation kind of law there. And so in that case, what my work does is it basically says, well, can we use like a combination of techniques traditionally used in optimization, things like variable reduction, to have our neural network output sort of a minimal set of variables that represent the outputs of our optimization problem? And then can we solve for all of the other variables actually using the constraints that we already know about, and then back propagate through this entire thing so that our neural network, when outputting this initial set of variables, understands how is my output going to be, used to solve for the full set of physical quantities? What is the quality of that full set of physical quantities? And then how do I then adjust the neural network outputs to deal with that whole thing? So that's one example. Another example is one where we're trying to basically control an inverter, for example, some kind of component on a power grid, but we want to maintain a particular notion of stability from the control theoretic perspective called Lyapunov stability. And so we basically provide a way to say we have a reinforcement learning algorithm that's going to make some kind of proposal of the action that can be taken by our inverter, for example. And then we project that action onto a set of actions that we know will stabilize the grid. And we kind of derive that set of actions using control theory. And then we are able to differentiate through that projection in a way such that, again, the neural network understands how its output's going to be modified so it can improve the quality of the action that it suggests that the inverter or the battery take. So those are just some examples of the kinds of constraints. The other question you had asked was about sort of usability, right? So how are people actually able to use these kinds of tools, and how does that play out? So right now, I would say in power grids, there's this tricky notion that a lot of the software that is used by power system operators is not developed in-house. It's developed by these like solutions providers who are developing software for them. There aren't that many of these software providers in the world, because if you think about it, there are only a few hundred power system operators in the world. And if you're a company that's vending to power system operators, the number of customers that you're vending to is not that large. You're not going to get this high growth, unicorn kind of company by giving software to power system operators. And so in some sense, for the power system operators, as long as the software works well, in theory, that's good enough. But the metrics for what it means to work well haven't adapted to sort of the AI era, where before you could assume that your optimization algorithms would satisfy certain things, and now you can't necessarily. So those metrics haven't been adapted. But then there isn't much capacity at these existing software vendors, because they haven't been making much money. In some sense, they've even been laying off their people to just like squeak by and maintain the power system optimization software at the minimal level. So this is actually a situation where there are, in theory, people with the technical skills who would understand how to implement these things. And there are people who they really just care about the metrics. They don't care about the internals, but both the metrics are a bit in flux, and the sort of capacity and in-house talent to actually implement some of these new things are in flux. So.
Yeah, interesting. One thing I wonder about, and I see this in my own work, I used to do a lot of work on automated diagnosis of electromechanical systems. And of course, like power grid optimization, or a lot of these problems have been around for a long time. They're costly problems, and they're problems that relate to our infrastructure. And so there are techniques that exist in-house already for doing some of these things. I was wondering whether, just sort of for the edification of the group here, whether you can sort of talk about what machine learning brings to these problems over and above the standard techniques that have been the sort of tried and true, when I say that in scare quotes, techniques that have been used for years and years to sort of try to address these problems.
Yeah, it's a great question. So some of the kinds of benefits that exist are, but of course, like should be thought about, does this benefit justify the method and so forth always, in a lot of, prediction workflows where you might have done this using a physical model before, it's the ability to ingest heterogeneous kinds of data that I think are kind of one benefit. So if you think about, like, I have an image of, I have a camera pointing at the sky telling me how clouds are moving, and I want to use that to predict how much solar power my solar panel is going to produce. How do you embed that into a physical model, the kind of image of how much cloud cover there is? You can try to quantify it and say maybe there's some kind of shading and so forth. But in cases where those kind of relationships are not so easy to write down, and you just in some sense want to be able to ingest these heterogeneous types of data without writing down the rules yourself, I think that can be a place where AI and machine learning can, provide some kind of benefit. And then in the optimization and control settings, in some ways, I think it's similar. It's a setting where you have kind of physics that you've written down to synthesize your robust controllers, or to actually solve your optimization problem. But in those cases where your physics and your assumptions might actually be slightly wrong, your data might be telling you something that your physical assumptions are not, and you want to somehow combine, what is my data telling me about what the system actually looks like versus what I think it should look like? And how do I kind of reconcile the system based on that? So I think these are a couple of ways in which, the sort of data-driven methods can provide some benefit. And you'll notice that in both of those cases, I never said throw out the old stuff and bring in the data. I think it really is a recognition of what is it that the data and the data-driven methods are bringing newly, and what is it that the existing methods are already giving us, and how do you kind of combine these kinds of methods to get the strengths of both?
Yeah, I agree very much with that philosophy. And I really liked your example of cloud cover as well, because I think, we are limited by the languages that we use to build these models, and they are languages of some form. And there's certain things, that we perceive as human beings, like clouds moving through the sky, that are just impossible to describe, and so they're hard to incorporate into our models. And so we need to use data and these sophisticated functions to recognize and classify and incorporate them into what we're doing. Yeah, it was a great answer. Thank you. I see there's a whole bunch of traffic which I was not reading because I was listening to what you were saying in the chat. Maybe we can just pause for a minute. And I'd like to invite anybody who was an author of any of this just to speak up if they'd like to pose their question for the broad audience.
Yeah, so for example, I see a question from Monica. I don't know if Monica, you want to verbalize it, or I'm happy to read it for you, whichever you prefer.
Yeah, sure. So thank you so much for this amazing presentation. It was very insightful and I learned a lot. So I am a student in the Master Information program. Through the program, we can explore different avenues, and there's also this option for doing a collaborative specialization in another field. And one of the options is environmental studies. So I'm taking that pathway, and my concentrations are UX design and info systems and design. And when you were talking about applications of AI to climate change, that really gave me some insight, because for years I was wondering, how can I use computer science to help the environment? And so I was thinking about I was considering maybe looking for opportunities at climate change AI. So yeah, I just wanted to ask about the opportunities that are available, and if we need to have prior knowledge of ML or AI for these opportunities.
Yeah, that's a great question. So there are a couple of ways to sort of plug in. So one of those is if you're looking for, as you said, co-ops or those kinds of opportunities. Climate Change AI has a newsletter and a community platform that have a lot of different job postings. So that's definitely something to take a look at. Are there any of those kind of jobs or internships or things in topics that you're interested in? We also, when we run our kind of workshop series at the machine learning conferences, we also run mentorship programs alongside those to basically pair people who, maybe are coming in with one person, usually will be somebody coming in with more of a climate change related background, say, and somebody else comes in with more of an AI related background, and one of them is the mentor, one of them is the mentee, but we pair them so that they can actually work together to develop something together. So to your question, do you need prior experience in climate change to really start jumping in? No, right? You kind of get experience by reading, by trying these things out, by kind of diving in. And so we definitely encourage that.
Oh, awesome. So we get experience on the job, basically.
Yeah. And that's, for me too, my background is computer science, and I work on, AI and machine learning in power grids. And I definitely learned a lot of that, just by going forth, by of course, reading and listening to people and doing all that stuff, but you do tend to gain a lot of it on the job. We also, by the way, have virtual happy hours where you can go meet people and potentially find other collaborators. That's another way to potentially plug in.
Awesome. Yeah. Thank you so much.
Yeah.
I'll keep those in mind.
Yeah, for sure. All right. So there's a question from Harshit, which again, Harshit, if you want to verbalize it, please feel free.
Yeah, sure. And thank you so much for a great talk. So I am wondering that so you have mentioned about integrating these climate constraint in the neural network, but I'm wondering how we can make sure that they are in a way that they can be differentiated. So if you can briefly talk about that.
Yeah, that's a great question. And so one keyword I'll drop here that might be helpful is this keyword called implicit layers. And there's a sort of tutorial from, now I forget what year it was in, but basically my former advisor, Zico Coulter, among others, kind of put that tutorial together, as well as David Duvenon at U of T, put that together to basically talk about how this works. But the way to think about this is most kind of standard layers in neural networks are what we would call explicit function. I think I got muted. Am I good now? Okay, cool. most functions that we think, layers that we would think about in neural networks are explicit functions. So one where you have a function, you kind of stick your inputs in on one side and your output kind of spits out the other side, kind of a explicit function, explicit equation. But when we think about a lot of these kinds of constraints that we want to enforce, they tend to be implicit functions, which is to say you can put in your, your independent variables, and your dependent variables don't naturally just fall out. You can't solve for them. You might need to use some kind of numerical method like Newton's method to do this. And so what the implicit layers literature says is, how do we actually deal with functions that look like that and actually figure out how to take derivatives through functions that look like that in a way that allows them to be embedded within neural networks. And what it basically relies on is something called the implicit function theorem, which basically says that if you have an implicit function like that and you've solved it, you are at the solution point, then you can actually differentiate through that equation at the solution point, kind of in the intuitive way that you would expect. Basically, you can think of your independent variables and your dependent variables as being related in a way that just allows you to take derivatives through that equation. And so this plays out differently in different places. So some of the stuff that I've been doing is differentiable optimization layers. So specifically optimization as an implicit function. And there you think about what are the equilibrium conditions of my optimization problem? Well, there's something called the KKT conditions that I can use as my implicit equations and differentiate through them. So you can get into your thoughts about if you have a specific type of implicit function that's encoding a specific type of constraint, what does it mean to differentiate through that? And so my work is thinking about this in the context of optimization, but the key word is implicit layers or implicit functions to think about how this actually works.
Yeah, thanks a lot. This is so interesting. I will look into it.
Yeah, for sure. Cool. And then I think Jillian is mentioning another kind of ongoing challenge right now about the AI for Global Climate Cooperation Challenge that's ongoing. So I don't know, Jillian, if you want to say more about that.
Great. Yeah, I was probably wondering if this is something that you're working with, Priya, or you I assume you are. I am actually I'm advising, reviewing, but I'm kind of just been leaving it off to one side, but I want to make sure people know about it. So this is using the same kind of multi-agent simulations that Salesforce folks have done with tax policy and looking at climate policy agreements. So anybody who's interested in this area, maybe and if you're involved, if you have thoughts about the opportunities for that and what your hopes are for it.
Yeah, it's a great question. So I'm not directly involved in the challenge itself, but I think it's definitely something very interesting that folks should consider checking out. I think with any challenge, right, it's of course important to think about, imagine we solve the challenge, what happens next, right? So how does the result of this actually get used? And so in this case, how does this actually go on to inform, for example, global policy negotiations? And I think that basically should be something that's at the forefront of people's minds in terms of how do I approach this? To what extent is this a simulation versus real? But what are the insights I glean from maybe participating in this that enable me to think about how do I actually then go on and influence or think about these global policy negotiation processes. So I think it's a really cool challenge. But of course, with any challenge, this is the question to be thinking about. If it gets solved, what actually happens kind of in the real world? And if it's sort of trying to shed insight on a real world process, what insights can we glean, even if the solution itself isn't the thing that's directly being applied, that we can then, think about how to embed in the real world. So, but yeah, definitely a challenge I would suggest people check out.
Yeah. I mean, and another direction to perhaps think about, I mean, you talked about systemic effects and sort of some of the unpredictable, whether the social dynamics that you trigger off or the power relationships. Could be interesting to think about how access to AI, access to compute, access to data, and so on in the context of global negotiations and setting of the terms and treaties and so on. How might that play out? I've been thinking a lot about the compute inequality that we're sort of facing in so many different domains, that you get a lot of optimization on one side of a problem, and you don't have a lot of optimization on the other side. Even thinking about scheduling of retail workers, right? Didn't require AI, but when we started optimizing on that, we created terrible lives for a lot of people who work retail kind of jobs.
Yeah, definitely. And I think that's the reason I'm always like excited to speak in sort of interdisciplinary fora like this one, because of course the technology problems, the social problems, the policy problems are really deeply interlinked and have, you know, various kinds of feedback loops and things among them. And so of course that question of, you know, who gets to use optimization models, like is it the retail workers or is it the retailer, is not just a technology question, but it's also a question of, you know, how our labor laws look and things like that. And so I think really always keeping, right, to me also, like it's important to think about, like keep in front of mind, how do these things, you know, interchange and interlink with each other? And as a result, how do we kind of on multiple fronts kind of make the kinds of changes that are necessary for the technology outcomes and the societal outcomes to basically align in a way that we would like. So
Yeah. Here. And on that important and inspiring note, I see Steve has his hand up, but Steve, I think I'm going to draw the official part of this talk to a close, and maybe Priya can stay on for 5 minutes more, Steve, to answer your question. I'd like to again thank Priya for a wonderful presentation. We really appreciate you taking the time to speak to us on such an important and thought-provoking topic. Next week's seminar will feature Barbara Gross from Harvard University. That will be on October 12th on discussing fostering responsible computing research. And I also wanted to give a heads up to everybody. We've mentioned this before, but on October 19th, we have a very special seminar series event with Gillian Hadfield, Director and Chair of the Schwartz Reisman Institute and Professor of Law at the University of Toronto, and who we just heard speaking. This is going to be an in-person event at the University of Toronto Faculty Club. And we're really hoping that it's going to be an opportunity for us to bring some of our community together in person for one of our seminars. Gillian will be talking about judging facts, judging norms, training ML models to judge humans requires a new approach to labeling data. So stay tuned for that. There will be registration information coming up. And please join me now in thanking Priya for a really terrific talk. Thank you, Priya.
Thank you all. Thanks for the great discussion.